Tell Winston Churchill that a soldier with a headset and a small machine assembled from commercial parts could hunt a tank several miles away. Tell him that an unmanned speedboat could threaten a warship without placing a sailor on board. Tell him that aircraft costing only a fraction of a missile could force entire cities, military bases and fleets to reconsider their defences. Churchill would almost certainly want to know one thing first. Which nation understood the change before everyone else? Because military revolutions rarely announce themselves with a single invention. They appear when technology, industry and strategy suddenly combine and make the old rules dangerously incomplete. That is what is happening now. The drone is not merely another weapon added to the battlefield. It is becoming part of a larger system that can observe, identify, track and attack. It can remain overhead while soldiers hide below. It can turn an ordinary road into a monitored corridor and expose a vehicle minutes after it begins moving. And unlike many previous military technologies, drones are not limited to the richest nations. Their essential components are already produced for a global civilian market. Cameras, batteries, navigation systems, communications equipment, processors, and lightweight airframes. The same industrial world that builds products for photographers, farmers, and delivery companies can also supply the foundations of a new military arsenal. Precision strike, once largely reserved for advanced air forces and expensive guided weapons, has become available on a far smaller scale. That does not mean a cheap drone can replace every missile, aircraft, or artillery system. Payload, range, weather, electronic interference, and reliability still matter. A small quadcopter cannot produce the destructive force of a large bomb, nor can it perform every mission of a combat aircraft. But it does not need to. Its revolutionary power comes from being affordable enough to lose, simple enough to modify, and numerous enough to appear almost everywhere. The war in Ukraine has made this transformation impossible to ignore. When Russia launched its full-scale invasion in February 2022, much of the world expected the conflict to be defined by familiar images: columns of armoured vehicles, artillery batteries, fighter aircraft, and infantry fighting across cities and open terrain. All of those forces remained important. Yet above them, a second battlefield began to take shape. Small reconnaissance drones searched for vehicles, trenches, and artillery positions. Commercial quadcopters helped units correct mortar and artillery fire. Larger unmanned aircraft conducted surveillance and attacks at greater distances. Then FPV drones began spreading across the front. FPV means first-person view. The operator watches a live video feed transmitted from the drone's camera, steering the aircraft as though sitting inside it. Many of these machines were adapted from civilian racing drone technology and fitted with explosives for one-way attack missions. They were not perfect weapons. Their signals could be jammed. Their batteries limited their range and flight time. Weather could disrupt operations. Pilots required training. Some aircraft failed before reaching their targets, while others struck without causing decisive damage. But their low cost and flexibility made them useful on an enormous scale. An FPV drone could fly toward a vehicle, enter a damaged building, follow troops along a road, or approach a position from an unexpected direction. A reconnaissance drone could locate the target. Another system could relay its coordinates, and an FPV aircraft could attempt the strike. The battlefield was beginning to operate as a connected network. This was a deeper change than the arrival of a new type of ammunition. For much of modern military history, a soldier could hide by moving beyond the observer's line of sight. Trees, buildings, hills and distance created protection. Commanders could gather forces behind the front before sending them forward. Drones weakened that protection. A small aircraft above the battlefield could look behind a wall, over a tree line, or into a trench. Thermal cameras could observe movement in darkness. Recorded footage could be examined by intelligence teams or distributed through digital command systems. The sky itself was becoming an observation post. That produced a frightening tactical equation. If a unit could be seen, it could often be tracked. If it could be tracked, its location could be transmitted. And once its location was known, artillery, missiles, or attack drones might follow. In previous wars, reconnaissance and attack were frequently separated by long chains of command. An observer found a target. Information traveled to headquarters. A decision was made. A weapon was assigned. By the time the strike arrived, the target might already be gone. Digital networks and unmanned systems can compress that process. Minutes become crucial. Sometimes seconds do. The result is not a transparent battlefield. War remains full of deception, confusion, and incomplete information. But concealment has become more difficult. Movement requires greater planning. Vehicles need camouflage. Command posts must control their electronic emissions. Soldiers must consider not only what can be seen from the ground, but what may be watching from above. Even evacuation and resupply have become more dangerous. A truck carrying food, ammunition, or fuel may not look strategically important. Yet an army cannot continue fighting if its supplies do not reach the front. Drones can search roads, follow vehicles, and expose routes that were previously considered relatively safe. This reveals one of the most important lessons of the drone revolution. Its influence is not measured only by the number of targets it destroys. A drone can change behavior without firing at all. The possibility of being watched forces soldiers to disperse. It delays movement. It requires additional camouflage and air defense. It consumes electronic warfare resources. It can make a valuable system remain hidden instead of performing its mission. That is military power expressed through uncertainty. The same principle has appeared at sea. For centuries, naval warfare demanded ships capable of carrying crews, weapons, fuel, sensors, and protection across hostile waters. Naval power was expensive because the ocean punished weak engineering, and because every vessel had to keep human beings alive. Uncrewed surface vessels changed part of that calculation. Ukraine, despite lacking a traditional fleet comparable to Russia's Black Sea Fleet, developed explosive unmanned boats that could travel toward naval targets under remote control. These vessels were relatively small, difficult to detect, and did not risk a crew during the attack. Combined with cruise missiles, intelligence, and other forms of pressure, maritime drones damaged Russian vessels and contributed to a much more dangerous operating environment for the fleet. Russia still possessed warships, submarines, aircraft, and coastal defenses. Sea drones did not erase conventional naval power, nor did they single-handedly decide control of the Black Sea. But they demonstrated that a weaker naval actor could impose serious costs without building a symmetrical fleet. A country did not necessarily need a cruiser to threaten another cruiser. It could combine intelligence, missiles, and unmanned systems, forcing a stronger fleet to reconsider where its ships were based and how they were protected. Churchill would have immediately understood the strategic significance. He had served as First Lord of the Admiralty and spent much of his career thinking about sea power, technological experimentation, and the vulnerability of maritime supply. During the Second World War, Britain depended upon Atlantic convoys for food, fuel, weapons, and raw materials. If the shipping lanes had been severed, Britain's ability to continue the war would have been placed in mortal danger. To Churchill, a weapon that could threaten ships without risking a crew would not have appeared as a curiosity. It would have appeared as a new instrument in the ancient struggle between maritime access and maritime denial. But the drone revolution is not only about airframes and explosives. It is also a contest over the electromagnetic spectrum. Most remotely controlled drones depend on some form of communication. Operators send commands. Aircraft transmit video. Navigation systems use satellite signals. Every connection creates capability, but potentially also vulnerability. Electronic warfare systems can interfere with control links, disrupt navigation, or help locate operators. Jamming may cause a drone to lose its video feed, miss its target, or become unable to continue its mission. This has created a continuous struggle between attack and defense. One side changes frequencies, the other develops new jammers. Operators introduce alternative navigation methods. Defenders search for new ways to detect them. Software is updated. Antennas are modified. Procedures change. A useful system may become less effective within weeks or months as the enemy learns how it works. More recently, fiber optic controlled FPV drones have demonstrated one method of avoiding conventional radio frequency jamming. Instead of depending entirely on a wireless control link, these aircraft unwind a thin physical cable behind them during flight. The method introduces its own limitations. The cable can become caught or broken, and the system creates logistical complications. Yet it illustrates the pace of adaptation. Every defense encourages a new form of attack. Every successful innovation begins a countdown to the enemy's response. This is why the war in Ukraine has become not only a battlefield, but an enormous and tragic laboratory of military change. Soldiers, engineers, volunteers, technology companies, and government institutions are working in overlapping cycles. Feedback may travel directly from a drone unit to a workshop. A component can be replaced, a design modified, and a new version returned to the field. Traditional defense procurement often takes years. On an active drone battlefield, useful improvements may be required far faster. That speed favors organizations capable of learning from failure. It also changes the meaning of military industry. During the Second World War, industrial strength could be measured in tanks, aircraft, ships, trucks, artillery pieces, and millions of tons of steel. Britain, the United States, Germany, and the Soviet Union understood that courage alone could not sustain industrial war. Factories mattered, energy mattered, supply chains mattered, standardization mattered, production mattered. Churchill understood that speeches could strengthen a nation's will, but factories had to arm it. The same principle survives today, although the materials are changing. Modern drone production depends on batteries, cameras, processors, motors, radio components, antennas, sensors, and software. Many of these products come from international commercial supply chains rather than traditional state arsenals. This creates both an advantage and a vulnerability. Civilian industry can provide enormous scale and rapid innovation. A component developed for entertainment, agriculture, or photography may quickly acquire military value. But dependence on foreign suppliers creates strategic risk. If one country controls the production of essential motors, batteries, or electronics, another nation may discover that its drone program relies on a potential adversary. The drone race is therefore also a supply chain race. Who can manufacture at scale? Who can replace losses? Who can secure critical components? Who can update software quickly? Who can teach thousands of operators? Who can produce not one perfect aircraft, but hundreds of thousands of useful ones? This is where the economics become disruptive. Military organizations traditionally value sophisticated platforms designed to survive for years. Those systems remain necessary. Nations still need aircraft, ships, armored vehicles, satellites, and long-range weapons capable of performing missions small drones cannot. But a mass-produced drone may be treated differently. It can be designed with the expectation that it will not return. Its value may come not from surviving numerous missions, but from being cheap enough to send in large numbers. This creates an uncomfortable exchange rate problem. If a defender uses a very expensive missile to destroy a much cheaper drone, the interception may be tactically successful but economically difficult to sustain. Yet allowing the drone to pass may place a far more valuable target at risk. The defender needs options at multiple price levels: jammers, guns, interceptor drones, directed energy systems where practical, traditional missiles, and passive measures such as camouflage, dispersal, and hardened shelters. There is no single answer because there is no single drone threat. A commercial quadcopter above a trench is not the same problem as a long-range one-way attack aircraft approaching a city. An unmanned boat is not defeated in the same way as a reconnaissance drone. A swarm would create different demands again. This is why counter-drone defense has become a strategic priority across NATO and beyond. The United States Department of Defense has warned that unmanned systems are becoming more capable, affordable, autonomous, and networked. NATO nations are testing detection systems, electronic defenses, and low-cost interceptors. Militaries are trying to avoid a future in which the weapon is inexpensive, but every method of stopping it is not. The lesson is larger than drones. War has entered a period in which adaptation may matter as much as possession. A nation can begin a conflict with advanced equipment and still fall behind if its procedures are too slow. Another may start with fewer resources, but improve rapidly through battlefield experience, flexible production, and close cooperation between soldiers and engineers. Churchill would have recognised this competition. Before and during the Second World War, Britain invested in radar, scientific research, intelligence, and code breaking. Churchill did not personally create these technologies, and their achievements belong to vast teams of scientists, engineers, military personnel, and intelligence officers. His importance was political and strategic. He understood that unusual ideas sometimes deserve protection, that scientific talent could have military consequences, and that institutional resistance could become dangerous during a national emergency. He also made mistakes. Some of his enthusiasm for unconventional projects did not produce useful results. Innovation is not the same as wisdom, and technological ambition does not guarantee strategic success. But Churchill rarely believed that tradition alone could protect Britain. Faced with today's drone revolution, he would probably not ask whether unmanned systems were honourable, elegant, or compatible with an older image of warfare. He would ask whether they worked. He would ask whether Britain could produce them. He would ask how the enemy might defeat them. And then he would demand another version. Yet the most important conclusion would not be that drones have made every older weapon obsolete. Tanks still provide protection, mobility, and firepower. Artillery still delivers effects that small drones cannot match. Aircraft still carry larger payloads over greater distances. Ships still provide air defense, strike capability, logistics, and command functions. But all of them must now operate in a world where inexpensive machines may be searching for them. Armour needs protection from above. Warships need defences against unmanned threats at sea and in the air. Infantry units need electronic warfare support. Headquarters must manage their signals. Supply lines must assume they are being observed. And commanders must integrate unmanned systems with artillery, intelligence, cyber operations, space-based surveillance, and conventional forces. The drone is not ending combined arms warfare. It is forcing combined arms warfare to evolve. That distinction matters. Every revolutionary weapon produces exaggerated predictions. The tank was once expected to make infantry irrelevant. Strategic bombing was supposed to decide wars on its own. Nuclear weapons led some to believe conventional conflict had become impossible. History was more complicated. New technologies did not erase warfare's older dimensions. They changed the relationship between them. The same will be true of drones. Their greatest influence may not be the destruction recorded in dramatic videos. It may be the quieter transformation of how armies move, hide, communicate, manufacture, and think. For Churchill, this would have been the real warning. The danger is not that a new weapon appears. The danger is that institutions continue preparing for the previous war while an adversary builds the next one. Industrial strength still wins wars. But industry no longer means steel alone. It means processors, batteries, cameras, secure communications, algorithms, trained operators and factories capable of changing designs almost as quickly as the battlefield changes its demands. The battlefield is no longer dominated simply by whoever possesses the largest army. Increasingly, it belongs to whoever learns and adapts fastest. By the summer of 1940, Britain was preparing for an attack unlike anything in its history. France had fallen. German forces controlled much of Western Europe. The British Army had escaped from Dunkirk, but it had abandoned enormous quantities of equipment. Across the English Channel, German aircraft gathered for a campaign intended to destroy Britain's ability to resist. The Battle of Britain was fought by pilots in the sky, but it was understood through information on the ground. Britain's radar stations detected incoming formations before they reached the coast. Observer corps posts tracked aircraft after they crossed inland. Reports passed through an organised command system that helped controllers decide where fighter squadrons were needed. Radar did not shoot down German bombers. It allowed Britain to use limited fighter forces more intelligently. That distinction offers the clearest answer to how Churchill might have used drones during the Second World War. He would not have viewed them simply as flying bombs. He would have seen them first as instruments of knowledge. Imagine small reconnaissance aircraft positioned along Britain's southern coast, not replacing radar, but working beside it. Radar could warn that enemy aircraft were approaching. Unmanned cameras might help identify formations, observe damaged airfields, or inspect coastal areas too dangerous for routine human patrols. After an air raid, drones could examine runways, fuel storage sites, and damaged communications without exposing additional personnel. They could help determine which airfield was still operational and which required immediate repair. But their limitations would have been severe. The communication networks, satellite navigation, compact processors, and lightweight digital cameras that make modern drones practical did not exist. Any genuine Second World War equivalent would have been heavier, less precise, and far more difficult to control. So this is not a claim that Britain could simply have imported a 21st century drone fleet into 1940. It is a strategic thought experiment. If Churchill had access to modern unmanned systems, where would he have placed them? Almost certainly wherever Britain suffered from uncertainty. During the Battle of Britain, information was a weapon, because Britain could not afford to waste its fighters. A pilot sent toward the wrong location consumed fuel, lost time, and might be unavailable when the real attack arrived. Drones could have expanded the observation network. They might have watched ports and airfields in occupied France. They could have monitored the assembly of German aircraft and landing craft. They might have followed changes in coastal defences or provided images after British bombing raids. Yet drones would not have guaranteed victory. German forces would have attempted to jam their signals, shoot them down, capture their technology, and trace their operators. Germany would also have developed or copied unmanned systems of its own. That is the first rule of imagining any technology in a historical war. The enemy does not remain motionless. Every advantage creates a reaction. Every new capability becomes a target. Every secret begins moving toward discovery. Churchill would therefore have demanded more than the aircraft itself. He would have needed trained operators, secure communication links, replacement components, intelligence analysts, and a command structure capable of turning images into decisions. A drone that collects information nobody can interpret is not a revolution. It is merely another camera in the sky. The same principle would have been even more important in the Atlantic. Britain's survival depended on merchant ships crossing an ocean threatened by German submarines, surface raiders, and aircraft. Convoys carried food, oil, weapons, and raw materials from North America and other parts of the world. The Battle of the Atlantic was not a dramatic struggle fought in one place. It was a long campaign across enormous distances. German U-boats searched for convoys. Escort vessels hunted submarines. Aircraft patrolled sections of the ocean. Intelligence teams analysed intercepted communications. Weather, darkness, and the limits of radar created spaces where an attacker could disappear. The ocean's size was one of the submarine's greatest allies. Modern unmanned aircraft could have reduced some of that uncertainty. Long-endurance drones might have flown ahead of convoys, searching for surface submarines or suspicious vessels. Smaller aircraft launched from escort ships could have extended their visual horizon. Unmanned surface vessels might have carried sensors away from the main formation, making it more difficult for a submarine commander to approach unnoticed. In an emergency, a drone might have delivered a radio, medicine, or small piece of equipment to a damaged ship. It might also have acted as a decoy. An unmanned vessel transmitting signals associated with a convoy could have forced an enemy to reveal its position or waste time investigating a false target. But again, drones alone would not have defeated the U-boats. Anti-submarine warfare requires the detection of targets hidden beneath the surface. Sonar, radar, aircraft, escort groups, intelligence, code breaking, depth charges, improved tactics, and industrial replacement all contributed to the Allied campaign. A drone could have expanded the search. It could not have made the ocean simple. Churchill understood that technology produced its greatest results when combined with other capabilities. The importance of radar came from its integration with communications, observers, fighter bases, and command centers. Intelligence from Bletchley Park became valuable because military leaders could use it without revealing too quickly how it had been obtained. The machine was never the entire system. The organization surrounding it determined its power. That lesson would also have shaped Churchill's approach to strategic bombing. During the Second World War, bombers were sent across occupied Europe to strike industrial sites, ports, railways, and cities. Crews faced anti-aircraft guns, enemy fighters, weather and navigation errors. Targets could be difficult to identify, especially at night or through cloud. Modern drones could have assisted with reconnaissance before a mission and damage assessment after it. They might have examined air defense positions or monitored railway traffic. They could have helped identify whether a bridge was still usable, whether a factory had resumed production, or whether bombs had missed their intended target. That information could have reduced unnecessary repeat missions and improved planning. But the ethical problems would not have disappeared. Better surveillance does not automatically produce better judgment. A clearer image can still be misunderstood. Intelligence may be incomplete. Commanders may exaggerate the importance of a target. Civilian presence may be missed, ignored, or accepted as part of a strategic calculation. Technology can make an attack more precise. It cannot make the purpose of the attack morally correct. Churchill's own record on strategic bombing remains heavily debated. A modern Churchill with access to persistent surveillance would face the same fundamental questions. What constitutes a necessary military target? How much civilian risk is acceptable? Does striking an industrial system shorten a war or deepen the destruction without achieving the promised result? Drones would have changed the method. They would not have removed responsibility from the leader giving the order. Their most valuable use might have come before one of the largest military operations in history. By 1944, the Allies were preparing to return to Western Europe. Operation Overlord required a landing across the English Channel, the movement of enormous numbers of soldiers and vehicles, and the coordination of naval forces, aircraft, airborne troops, intelligence, and deception. The success of Normandy depended on understanding the coastline. Planners studied beaches, tides, obstacles, German fortifications, roads, and terrain. Reconnaissance aircraft photographed occupied France. Resistance networks provided information. Intelligence officers assembled countless fragments into a picture of the German defences. Modern drones could have made that observation more persistent. Small aircraft might have approached beaches at low altitude and photographed obstacles from multiple angles. Others could have monitored construction around bunkers or tracked troop movements near potential landing zones. Special operations teams and resistance groups might have used compact drones to observe roads, bridges, and railway junctions without approaching them physically. Immediately before the invasion, unmanned systems could have examined weather conditions and beach areas. After troops landed, drones might have searched beyond hedgerows, located defensive positions, and helped naval gunfire or artillery correct its aim. This could have reduced some of the uncertainty that made Normandy so dangerous. It could not have removed the danger itself. German forces would still have held fortified positions. Mines would still have covered approaches. Weather and sea conditions would still have mattered. Communications would still have failed. Units would still have landed in the wrong places, become separated, or misunderstood orders. Most importantly, German electronic warfare and air defences would have evolved in response. If drones had become common before 1944, the Atlantic Wall might have included specialised jammers, additional light anti-aircraft weapons, and camouflage intended to deceive cameras from the air. False vehicles could have been positioned along roads. Fake gun emplacements could have attracted drone reconnaissance. Signals could have been transmitted from empty locations. The Germans might have used drones to watch ports in southern England, search for landing craft, and challenge the Allied deception plan designed to conceal the location of the invasion. The presence of drones on both sides could even have made secrecy more difficult. Operation Overlord required the concentration of a vast invasion force. In a world of persistent aerial observation, hiding that concentration would have required an even more sophisticated campaign of camouflage, electronic deception, and false activity. The drone does not merely reveal truth. It creates another arena in which truth must be hidden. Churchill would have understood this from Britain's experience with intelligence and deception. Information had to be collected, protected, and manipulated. Knowing what the enemy could see was almost as important as seeing the enemy. For special operations, the advantages might have been more direct. British commandos and special operations executive agents operated in dangerous environments where a brief exposure could lead to capture or death. Compact drones could have surveyed a target before a raid, watched a road for approaching patrols, or examined a railway line from concealment. They might have carried small radios, documents, or medical supplies. Yet every transmission could betray the user. A drone signal might reveal the presence of an agent network. A crashed aircraft could expose its technology. Repeated flights around one location could lead security forces toward the people operating it. The machine might protect an operative from one danger while creating another. This pattern repeats across almost every possible Second World War application. Reconnaissance would improve, but so would counter-reconnaissance. Targeting could become faster, but deception would become more sophisticated. Some human lives might be protected, but new groups of soldiers and civilians would become vulnerable. Operations could accelerate, but leaders would have less time to question the information arriving before them. That final consequence may be the most important. Churchill conducted war through reports, maps, intelligence summaries, meetings, and direct communication with commanders. Information moved slowly by modern standards. Even urgent decisions could be delayed by distance and uncertainty. A drone network could have transmitted battlefield imagery almost immediately. Churchill might have watched an operation unfold from London. That sounds like an advantage. It could also have encouraged dangerous interference. A political leader observing a live video feed may believe he understands the battlefield better than the commander physically present. Yet the camera shows only what lies inside its frame. It cannot always reveal exhaustion, confusion, morale, or activity beyond the sensor's field of view. More information can improve command. It can also create the illusion of control. A Churchillian use of drones would therefore depend on discipline, knowing when technology should inform a decision and when it should not replace military judgment. That principle leads directly from the Second World War to the drone competition taking place today. Ukraine has shown the value of rapid battlefield adaptation and mass production. It has developed a diverse unmanned ecosystem ranging from small reconnaissance and FPV aircraft to long-range attack systems, naval drones, and increasingly capable ground vehicles. Russia has adapted as well. It has expanded drone production, developed new tactics, and invested heavily in electronic warfare. The contest is not between one innovative side and one static side. It is an accelerating struggle in which both search for temporary advantages. The United States is approaching the problem from a different position. It possesses advanced aircraft, satellites, ships, missiles, and global military infrastructure. Its challenge is not simply to acquire drones. It is to integrate large numbers of autonomous or semi-autonomous systems without sacrificing reliability, security, and command responsibility. American programs have explored the use of relatively inexpensive unmanned platforms that could operate across air, sea, and land. The underlying goal is to add mass without reproducing the cost of traditional crewed systems. A commander might use unmanned aircraft as scouts, communications relays, decoys, or additional weapons carriers. Uncrewed surface vessels might extend naval surveillance. Autonomous systems could undertake missions considered too dangerous, repetitive, or geographically dispersed for human crews. But the United States faces a difficult industrial question. Can it produce affordable systems at the scale required for a major war? A prototype can impress an audience. A military revolution begins only when thousands can be manufactured, repaired, updated, and replaced. China understands the importance of scale. Its civilian manufacturing base occupies a central position in the global drone supply chain. At the same time, the People's Liberation Army is investing in artificial intelligence, robotics, unmanned aircraft, maritime systems, and the networks required to connect them. In a potential conflict in the Indo-Pacific, geography would make unmanned systems especially important. Vast distances, contested islands, and threats to major air and naval platforms could create demand for systems able to scout, relay information, confuse defences, and impose costs without placing a human crew on every platform. Yet China faces the same uncertainty as every other nation. Systems that perform well during controlled exercises may behave differently in a heavily jammed, rapidly changing war. Networks may break. Sensors may be deceived. Artificial intelligence may misclassify targets. Mass production cannot guarantee sound doctrine. Hardware without battlefield learning may produce only mass-produced mistakes. Israel has accumulated extensive experience with unmanned surveillance and strike systems. Its defense industries have exported drone technology to numerous countries, while the Israeli military has integrated unmanned aircraft into intelligence and operational networks. Turkey has also emerged as a major drone producer. Turkish systems gained international attention through their use in conflicts including Libya, Syria, Nagorno-Karabakh, and Ukraine. Their importance was not that one platform made conventional forces unnecessary. It was that drones became accessible to countries unable or unwilling to purchase the most advanced crewed aircraft. Europe is now attempting to strengthen its own capacity. The war in Ukraine exposed shortages in ammunition, production speed, and industrial readiness. European NATO members are investing in drones and counter-drone systems, but they must overcome fragmented procurement, slow approval processes, and dependence on foreign components. NATO's challenge is broader still. An alliance of many countries must make systems communicate with one another. A drone operated by one army may need to share information with another country's artillery, aircraft, or air defense network. Interoperability is not an administrative detail. It can determine whether information reaches the weapon capable of acting on it. Churchill would recognize the shape of this global race, not because it resembles the Battle of Britain in appearance, but because the strategic question is familiar. Can democratic nations identify danger early enough? Can government, industry, and science cooperate under pressure? Can promising technology move from the laboratory to mass production? Can alliances share information without becoming trapped by bureaucracy? And can leaders accept failure quickly enough to change course? If Churchill had possessed drones during the Second World War, he would have used them aggressively, but probably never in isolation. He would have connected them to radar, intelligence, naval operations, aircraft, artillery, commandos, and industrial production. He would have demanded speed. He would also have learned that speed creates new vulnerabilities. Because the real advantage does not belong to the nation that displays the most impressive drone at a military exhibition. It belongs to the nation that can integrate unmanned systems into the entire machinery of war and continue adapting after the enemy begins fighting back. Drones would not have guaranteed Churchill victory. They would have given him more eyes, more reach, and more choices. And in war, those choices can save lives. But they can also make destruction easier, decisions faster, and responsibility more difficult to escape. That is where the historical question ends, and the most dangerous question begins. What happens when the machine no longer waits for a human being to guide every movement? A drone controlled by a human operator is already a formidable weapon. A drone capable of navigating after losing its connection is more difficult to stop. A group of drones able to communicate, divide tasks, and change its behavior without waiting for new instructions would represent something more consequential. And a weapon capable of selecting and attacking a target by itself would cross a boundary humanity has not yet fully decided how to govern. This is where the drone revolution is heading, not toward a battlefield without human beings tomorrow morning, but toward a gradual transfer of functions once performed only by humans. Navigation, recognition, coordination, threat detection, route selection, and potentially decisions involving lethal force. Artificial intelligence is already useful because the modern battlefield produces more information than any human team can examine quickly. Satellites collect images, radar systems track objects, reconnaissance drones transmit hours of video, electronic sensors detect signals, soldiers report movements, cameras watch roads, buildings and defensive positions. The problem is no longer simply obtaining information, it is identifying what matters before the opportunity disappears. AI systems can help search large volumes of data, compare new images with older ones, and alert operators to possible changes. They may assist in recognizing vehicles, detecting movement, or identifying patterns that a tired analyst might miss. This does not mean the machine understands war. An algorithm can recognize similarities within data. It can estimate probabilities. It can recommend a route or highlight an object. But it does not experience fear. It does not understand surrender in the human sense. It cannot comprehend the life of a person standing beside the object it has classified. And it cannot carry moral responsibility. That difference becomes crucial when AI moves from supporting human decisions to making decisions about targets. Imagine a drone approaching an area where its communications have been jammed. A conventional remotely piloted aircraft may lose control and fail. A more autonomous system could continue toward a pre-selected location, navigate using stored terrain data, and search for an object matching a defined profile. That capability has clear military value. It also creates a dangerous question. What happens if the profile is wrong? A tank may be hidden near civilian vehicles. A soldier may be wounded or attempting to surrender. A school bus, agricultural machine or ambulance may resemble something contained in the system's training data, especially when seen through smoke, darkness, or a damaged sensor. Human beings make terrible mistakes in war. Autonomy does not invent error, but it can reproduce error at machine speed and potentially across many systems at once. This is one reason the United States Department of Defense requires autonomous and semi-autonomous weapon systems to permit appropriate levels of human judgment over the use of force. NATO's principles for responsible military AI emphasize lawfulness, accountability, explainability, reliability, governability, and the mitigation of bias. Those principles reveal the central problem. Military AI must operate in environments designed to confuse it. Civilian AI systems may fail when conditions differ from their training data. An enemy will deliberately create those differences. It will conceal equipment, manipulate signals, construct decoys, and attempt to corrupt the information on which the algorithm depends. A machine may perform impressively during testing and fail in a battlefield filled with smoke, debris, electronic interference, and deception. The adversary is not weather. The adversary is actively trying to make the system wrong. That is why the claim that fully autonomous AI weapons already dominate modern battlefields would be misleading. AI-assisted functions are expanding. Various weapons already contain forms of automation, and some systems can navigate, track, or respond to threats with limited intervention. But the image of independent robotic armies choosing and destroying targets across the battlefield without meaningful human involvement is not an accurate description of warfare today. The more realistic future is mixed. Human commanders will set objectives. AI will help process information. Crews may supervise groups of unmanned systems rather than pilot each one directly. Some machines will navigate and coordinate with limited assistance. Others will operate under tighter control because their missions carry greater legal or political risk. Traditional forces will continue to provide firepower, mobility, logistics, and command. The revolution lies in how all these elements are connected. This brings us to the idea of the drone swarm. The word often creates an image of hundreds or thousands of small aircraft moving through the sky like insects, overwhelming every defense through sheer numbers. That may eventually become possible in certain conditions. But a true military swarm is not simply a large number of drones launched at the same time. The more important concept is cooperation. One drone might search. Another could relay communications. A third might approach a suspected target. Others could change direction when a threat is detected or distribute themselves across an area without every movement being directed by a separate operator. If part of the group is destroyed, the remaining systems might reorganize. This would reduce the burden on human controllers and allow more machines to participate in an operation. Yet coordination creates new vulnerabilities. Drones need to communicate, or at least share some understanding of the mission. Those links can be jammed, intercepted, or deceived. Software can contain flaws. A navigational error may spread through the group. An attacker might attempt to insert false information into the network. A swarm does not eliminate command. It transforms command into software. And software can fail. The defensive response is already developing. Electronic warfare can disrupt navigation and control signals. Radar systems are being modified to detect smaller and slower objects. Cameras and acoustic sensors can help distinguish drones from birds or civilian aircraft. Interceptor drones can pursue hostile systems. Guns and missiles can destroy them. Directed energy weapons, including lasers and high-powered microwave concepts, may provide additional options in suitable conditions. Passive defenses remain important as well. Camouflage can make targets harder to identify. Decoys can attract attacks. Vehicles and personnel can disperse. Protective nets and physical barriers can prevent some small drones from reaching vulnerable points. Hardened shelters can limit damage even when interception fails. The best counter-drone architecture will probably combine several of these methods. No single defense is sufficient. Electronic jamming may work against one control system and fail against a drone using alternative navigation or a fiber optic connection. A missile may destroy a larger aircraft, but be too expensive to use against every small target. A gun may be economical, but limited by range, accuracy, or terrain. The defensive challenge becomes even harder when drones attack in numbers. A system that can defeat one target may become overwhelmed by 50. This creates a competition not only between weapons, but between costs. If the attacker can repeatedly launch inexpensive systems, and the defender must repeatedly use expensive interceptors, the attacker may gain an advantage without destroying the protected target. It can exhaust ammunition, force defensive systems to reveal their locations, disrupt operations, and impose a financial burden that becomes difficult to sustain. A Churchillian leader would recognize the industrial logic immediately. Britain did not survive the Second World War by seeking a perfect defense against every German attack. It built networks, dispersed production, repaired damage, and continued fighting. The future drone defense will require the same resilience. Airfields must remain usable after an attack. Communication networks need alternatives. Factories must be capable of replacing lost systems. Military units must function even when satellite navigation is unavailable. A nation that depends on one delicate network may discover that technological sophistication has created strategic fragility. But drones will not threaten only military forces. The same characteristics that make them valuable in war, low cost, accessibility, remote operation and precision, also make them attractive to terrorist and criminal organizations. A small group may not be able to acquire a fighter aircraft or a cruise missile. It may still be able to purchase civilian components, modify an airframe, and attack a public event, power facility, airport, or political target. This creates a serious security problem for open societies. Modern cities contain thousands of buildings, vehicles, and electronic devices. Civilian drones are used for photography, construction, inspection, agriculture, and entertainment. Authorities cannot treat every object in the sky as an enemy weapon. Detection is only the first challenge. A suspicious drone may be flying near homes, roads, or an airport. Jamming it could interfere with other systems. Shooting it down might cause debris or explosives to fall on civilians. Taking control of it may be technically difficult or legally restricted. The defender must decide quickly while knowing very little. Who launched it? What is it carrying? Where is it going? Can it be stopped safely? This is the domestic version of the same problem appearing on the battlefield. More information, less time, and enormous consequences for a mistake. Border security presents another dilemma. Drones can patrol remote territory, detect fires, locate missing people, and observe illegal crossings. They can reduce the need to send personnel into dangerous terrain. But persistent surveillance can also become an instrument of political control. A government capable of monitoring borders from the air may extend that monitoring into cities, protests, and private property. Cameras can be combined with facial recognition. Flight data can be stored. Individuals can be tracked without ever knowing they were observed. The drone is therefore not only a military question, it is a question about the future relationship between the citizen and the state. Churchill defended Britain against dictatorship, but his own political legacy contains contradictions and controversies. A modern Churchill would have to confront a problem that did not exist in the same form during his lifetime. How can a democracy use powerful surveillance technology without slowly adopting the habits of the regimes it opposes? National security requires information. Freedom requires limits. Technology makes it easier to expand the first while quietly weakening the second. The danger is rarely announced as tyranny. It arrives as convenience, temporary necessity, and one additional camera in the sky. Yet the future of drones is not solely a story of war and surveillance. The same technologies can save lives. After a hurricane, earthquake, or flood, roads may be blocked and communication networks destroyed. Drones can survey damaged areas faster than ground teams, search for survivors, and create maps for emergency services. They can inspect bridges, power lines, and buildings before workers enter unstable areas. They can carry radios, blood, vaccines, or other small medical supplies to isolated communities. Firefighters can use thermal cameras to identify dangerous hotspots. Rescue teams can search large areas without exposing pilots to smoke or severe weather. Farmers can monitor crops and apply chemicals more precisely. Engineers can examine infrastructure that would otherwise require dangerous climbs or expensive aircraft. An unmanned system can enter a contaminated environment where sending a human being would be irresponsible. It can monitor wildfires, search at sea, map a disaster zone, deliver equipment to a trapped team, and perform repetitive industrial tasks without risking a worker's life. The technology itself does not know whether it is carrying medicine or explosives. It does not know whether its camera is searching for a survivor or tracking a target. That decision belongs to the person, institution, or state controlling it. This is why saying that technology is neutral is only partly sufficient. A machine has no moral intention. But technologies are designed within systems of power. Their features, ownership, and rules determine who benefits from them and who becomes vulnerable. A drone designed for delivery can be modified for surveillance. A mapping system can produce targeting data. An algorithm trained to identify damaged vehicles may also be used to identify military ones. Civilian and military development increasingly overlap. This dual-use nature accelerates innovation because governments do not need to create every component from the beginning. They can draw from advances in commercial batteries, cameras, robotics, and artificial intelligence. But it also makes control harder. Components can cross borders. Software can be copied. Instructions can spread online. A capability once possessed only by states can become available to companies, criminal groups, and individuals. The democratization of precision is also the democratization of disruption. What, then, would Churchill warn us about? Probably not the drone itself. He lived through an era of rapid military transformation. He saw aircraft move from fragile machines to strategic weapons. He witnessed radar change air defense, code-breaking reshape intelligence, and nuclear research open the door to a weapon capable of destroying cities. He understood that refusing to study a dangerous technology does not prevent an adversary from developing it. A Churchillian response would invest in drones, artificial intelligence, electronic warfare, and counter-drone defenses. It would connect scientists with soldiers and strengthen the industrial base required to manufacture systems at scale. It would test aggressively, accept failure, change designs, train operators, protect supply chains, and prepare alliances to fight as connected forces rather than isolated national armies. But a truly Churchillian strategy would also recognize that machines cannot answer political questions. A drone can destroy a target. It cannot explain what victory means. An algorithm can recommend an attack. It cannot determine whether the war itself is wise. A swarm can overwhelm a defensive position. It cannot build a stable peace after the position has fallen. Technology can expand military power while leaving strategy empty. That may become the greatest danger of the drone age. As the distance between decision and destruction grows, war may appear easier to begin. Leaders may believe that unmanned systems allow them to impose costs without risking their own soldiers. Public resistance may weaken if fewer body bags return home. States may conduct attacks while denying responsibility. Machines may operate in contested areas where a single error could trigger escalation between nuclear powers. The initial political cost of using force may fall. The long-term consequences may not. And faster warfare may leave less time for restraint. If an AI system detects what appears to be an incoming attack, commanders may have only minutes to decide whether the warning is genuine. If autonomous defenses respond automatically, one mistake could provoke another machine's response. War has always contained accidents. The future could connect those accidents to systems operating at a speed human diplomacy cannot match. This is why human oversight cannot become a ceremonial phrase. A person approving an action must have enough information and time to make a real decision. If the machine presents only one recommendation, if the operator cannot understand its limitations, or if rejecting it is practically impossible, then the human may remain technically present while losing meaningful control. Responsibility cannot be transferred to an algorithm. A machine cannot be court-martialed. It cannot experience guilt. It cannot compensate a family. It cannot explain why it decided that a human being matched a target profile. The commander, designer, manufacturer, and political authority will still have obligations, even when responsibility becomes difficult to trace. Churchill's era teaches us that nations which ignore military revolutions often recognize their mistake only when the consequences arrive. Today's revolution is not occurring only in the sky. It is unfolding inside software, factories, communication networks, electronic warfare units, and artificial intelligence laboratories. Drones will not eliminate soldiers. They will change what soldiers must survive. They will not make tanks, ships, or aircraft disappear. They will force them to operate differently. They will not end the need for leadership. They will punish leaders who confuse technological novelty with strategy, and those who ignore technological change altogether. Tomorrow's battlefield will combine conventional forces with unmanned aircraft, robotic vehicles, maritime drones, satellites, cyber operations, electronic warfare, and AI-assisted command systems. Some machines will be controlled directly. Others will perform limited tasks autonomously, and the boundary between assistance and independent action will become one of the defining political and moral struggles of this century. The strongest nation may not be the one with the largest army, nor the one with the most expensive weapons. It may be the nation that can learn fastest, manufacture at scale, protect its networks, and preserve human judgment while its machines accelerate the war around it. Churchill never saw this battlefield, but he understood the mistake that could lose it. The greatest danger is not the drone. It is not even the algorithm. It is the confidence that tomorrow's wars will continue to obey yesterday's rules. Because the next military revolution will not wait for the world to feel ready. It has already begun.